It's a keep silence, or it's a quite different, whereby I feel that something is wrong there. Either saya ajar tak bagus, either you tak buat kerja, ataupun saya punya notes memang bagus, ataupun you ada previous lecture notes, which is senior punya notes lah. So there's a lot of possibility lah. I don't know what is that lah. I don't want to guess, but I hope that you have a lot of questions for me, that I'll be there. I'll be here to help you lah. So at the beginning, we talk about the design of PM machine, permanent magnet machine. In short, we call PMSM. In short, now we have another part of a machine we call induction machine, or we call induction motor. So working principle, the generator is a device convert mechanical energy to electrical energy. The relative motion between the conductor and the flux and the EMF induced in the conductor. I think that you may understand what is a Fleming right-hand rules, Fleming left-hand rules, whereby Fleming right-hand rules is F equals to VLR. We want to have three things. One, it must be a conductor. One, it must have a magnetic flux density. One is it must have a relative motion. Then we will have a force generator. Then this force generator, we call it a kinetic energy lah, whereby it is operate as a motor, which means we input current, then we get rotation. This is called motor. If let's say we rotate and then we get current, that is called generator, which is E equals to BLV. Under first conductor, second flux, third it must have a relative motion, then we will have a EMF. So this is the definition of a generator and a motor, whereby generator is a device convert mechanical energy to electrical energy. Motor is a device convert electrical energy to mechanical energy. That's it. So in an electrical machine, we have a DC machine, we have an AC machine. Why we call electrical machine? Because the machine are working as a electromagnetism, where it can be generator, it can be motor, it can be transformer. Why? Because it's played with a EM, electromagnetism, in between AC. So we have a DC machine, we have an AC machine. Then when DC machine, we also have a DC generator or DC motor, which I think you already learned in a 306. And then for the AC machine, we have a synchronous, we have a asynchronous. Synchronous means when we, if you still remember, when we want to run a motor or we want to run a generator, it must have two sources of fluxes. One is a stator, north and south pole. Another one is the rotor, north and the south pole. If let's say north, then it will repel. If let's say rotor part is like this, then it will attract. This one will be repel, this one will be attract. This is the basic principle. If let's say the rotor is running in here for the at this position, then this one is following the pole here, then we call synchronous. If let's say it is not synchronous, we call asynchronous. Asynchronous means not synchronous. Synchronous, we have a synchronous generator, we have a synchronous motor. In the generator, we have a one phase, we have a three phase, one phase, three phase, So I think PMSM is under synchronous machine. PMSM is under synchronous machine, whereby it can work as a generator or motor. Usually we don't focus in the generator because we seldom use generator, but we are usually more on the motor side. And then asynchronous is an induction machine. For sure, we still have a lot of motors, but we focus on here only. So introduction, what is the construction of the rotating machine? We have a terminal box, we have a cooling fan, and stator. Rotor. Stator means static part. Rotor means rotating part. Stator winding, the winding at the stator, drive shaft, and then the end, this is end. So we have a stationary part called stator. We have a rotating part called rotor. We have a shaft, we have a slip rings, we have a bearing. Slip rings brush assembly is something at here, but it happened on it's here. It's here. This is a slip ring. Huh? Then bearing is this one, no? Bearing inside. I'm not sure if you look through bearing or not. Look, bearing is something like this. When we have a shaft here, okay, when we have a shaft here, and then when we rotate this one, then this one no rotation. Or we rotate this one no rotation. This is called bearing, huh? Basic concept of a rotating machine design. The main purpose of designing a rotating machine is to obtain the complete physical dimension of all the parts of the machine to satisfy the customer specification. Last time when we did electrical machine, what we did is we only know how many horsepower we need to buy. For example, I want to start up a fan. My boss asked me to say, oh, I want to run maybe a fan application to make my room cool. So how many power of motor should I go for? Maybe we will say, we need to go for 1 horsepower. Or we will say aircon, aircon. Which horsepower is better for this size of room? Maybe it's 1 horsepower, maybe 1.5, maybe 2 horsepower. This horsepower is referred to the motor. Then the following design detail are required. What we need to do is main dimension of stator, detail of stator winding, design detail of rotor and winding, performance characteristics. These 3 of it, so that we can continue for the induction motor design. Remember, this topic or this following requirement are quite different with the PM/SM design of what you are doing in a mini project. Yeah, remember. And then this page is very important. Please jot down. Very important. So electrical motor specification requirement from the end user. Usually, if let's say when we go to the factory to do the motor fabrication, especially in Malaysia, at the Sprung Pride, we have one company called Teco. Teco is usually fabricate the induction machine either in a 1 phase, either in a 3 phase. Before fabrication, in Unimap, we use ANSYS to do the simulation. But induction motor is quite old technology. It's very old technology plus established. Established means I forgot to set time. Okay, so we start, we will end, we will rest or not end. And we will stop after 30 minutes. Maybe after 25 minutes. Okay, we're going to start already. Okay, we will rest for 10 minutes after 25 minutes. So for the induction motor, it's quite old and established. I mean, already matured. Matured. So ANSYS can be used to simulate the induction machine one, but it is quite slow. Another one is software is very good. We call MotorSoft. This one is industry always used to design the induction motor. For example, we just key in this one, anything. Then we just click. Okay, all the dimension will be come out. So just go through lah. Phase voltage, what we want to design is a 440 volt, 3 phase. Output power 30 kilowatt. Frequency 50 hertz. Number of pole, how many we want to do. What is the circuit connection we want? Either delta or Y. And then the magnetic loading, 0.48 Tesla. Magnetic loading means the electrical magnetic flux density in the mid air gap is in the middle of the air gap. Averagely they need 0.48 Tesla. Specific electrical loading. Electrical loading means electric current or charge that happen in the stator winding. Winding. So this is on winding side. This is inside the motor. Inside motor. For example, this is my rotor, this is my stator. Let's say so my stator, maybe this one. This is my stator. So this is the middle of the air gap. Middle of the air gap. Okay. Then we will see how many the magnetic loading. Then if let's say we draw the current, okay, how high the current can go. And then full load efficiency. Full load efficiency means P in go into the stator, then P out how much we have. So maybe we have a 0.88%, 0.88 or 88%. Power factor. So power factor loading, right? Because we have a reactive and active power. Okay. So when we put something clamp in on the shaft, what is the effect on the primary side? And then a primary side, winding side. Then the winding factor. Everything are given. Everything are given. But we need to know how to use a formula to calculate the dimension. Okay. From this information. So for example, stator, rotor, then output power, this is the formula, output coefficient, and then formula. Don't ask me how can I get it. It is derived. I take it from a book, but I don't know where is the book from. Because this slide is come from other the previous lecture. So we have a length, we have a diameter, so we have a length. Where's diameter? Diameter, length. This is how we want to do lah. And then we also need to know what is the formula is that. For example, CO is a coefficient. So go back, where is the CO? Sorry, CO is calculated from here. So if let's say we want to get CO, right, in order to input here, so we need to find BAV. So our BAV is here. This is our BAV. So we input the BAV. What is a Q? So where is a Q? Q is here. So we input this value. So what is a KW? KW is here. So we use this value. And then what is the efficiency? Efficiency is a 0.88. And then power factor. So it's from power factor. Okay. And then we will get our CO. C naught. And then diameter given. Diameter is given, is it? No. Diameter is not given. We need to find the diameter. So this is the final equation we need to find. So the first one, we need to find CO. CO is this one from the given. And then CO can be brought down. And S is the slip. Where is the slip? Where's the slip? And S is synchronous speed. And S is the synchronous speed. And S is the synchronous speed. We need to use F equals to MP over 120. This is NS. P is the number of pole pair, 120. Frequency is 50 Hertz. This is 50 Hertz. Okay. Then, okay, at the very beginning, I told you that the P is a pole pair. This is a number of pole, not pole pair. P is a pole pair where a number of pole divided by 2. But this is a small p. For the capital P, it is a number of pole here. So don't get confused. So after we have this all information, we can get this one. And then length will be given with the pole number, we will get our D. So we have, because it is a square, we have two possibilities. One is positive, one is negative. So we take the positive one, substitute here, then we can calculate from this equation. Then K and W are given there, then we will get our Q. Maybe like this. I forgot how to use the equation already. I will show you applying on how to use the equation. No worry, no worry about that. Just have a look and get know that you come across that you have this type of equation. And then we also have this type of equation where you have learned it from the analytical calculation, number of turns per phase, flux per pole, everything. Just use it. Just use it. Same as well here. Just use it. Later I will go. We will discuss on the example. Directly apply it. Directly apply it. This is one of the example. You can go back and have a try. I won't tell. I won't tell you the answer because I don't have the solution here. But I have. If not mistaken, I have an example tutorial. Later I will go into that. Same thing in the sense of we have all these different values, and then this is the main dimension that we need to calculate, whereby we need to use all the equation here, and here. After that, example same as well. Yeah, that's it for the this one. I think I will go to let me close my stop sharing first. I open up the tutorial. I think I will go to example tutorial. Where is it? Ada tak sini? Ada. Okay, let me share screen. So actually we finished all the lecture, We already finished all lecture. Okay, so can I proceed or not? Or you want to have a rest? Guys, can I proceed? Blah, 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 blah. Right, guys. Can I proceed or do you want to have a break? Right, let me see where is the message. Proceed. Okay, thank you, Aiman. Let us proceed, So just now, why I go so fast, because I don't think that is important for us to memorize. You don't need to memorize at all. This one won't come out in the final exam or OBE. Last time, yes, it come out in final exam. But this is under problem-based learning. What you need to do is you use back this calculation and do your uh, 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 solution. Okay, so just now what we saw from the example is in the table type lah. Let me show you the table type form. It is table type form, but I won't do that lah. In here, I will just make it simple. So design an induction machine. We call induction motor. In terms of the main dimension of the stator, number of turns per phase, number of stators pole, slot, and the conductor per slot according to the specification as below. So first of all, it must have a 50 kilowatt. Supply power is 440 volt, 3 phase, 8 pole, 60 hertz, delta connected, and then it is a squirrel cage induction motor. And then assume number of slots per pole per phase is 3. Assume which means it's already given. For example, this one it already given number of this one not given. This one need to calculate number of pole per phase. So and then magnetic loading is 0.52, electrical loading is 20k, full load efficiency is 0.93, full load power factor 0.81, and winding factor 0.921. So what we need to do is first of all we need to estimate what is a C naught. When we want to try to do the C naught, we need to get this value actually. So first we need to settle C naught. Just apply the formula 11 BAV Q KW. So BAV is 0.52 from here, okay, 0.52, and then Q is 20,000, KW 0.921, 0.93 is efficiency, this is power factor, which is from here, and then 10 minus 3 must be included. Why? Because the formula is like this. Okay. Yes, you see the formula is included 10 to power minus 3. Okay, so do the calculation, and then we want to find the synchronous speed because when we found the C naught, we need to find the NS synchronous speed. Wait. So we want to find the synchronous speed. Usually I will just put as F equals to NP over 120 lah. Then I know that this N is the synchronous speed, P is the number of pole, and then F is the frequency. So what we need to do is we need to find the synchronous speed. So I will put NS equals to 120 times F divided by NP lah, whereby so 120 F P, and then why we need to divide by 60 funny. Oh, why we need to divide by 60 I don't think we need to divide by 60 this is wrong no 60 no 60. This one is wrong. We need to do the recalculation. So let's say this is one value is of the 15 RPM. No divide by 60. Okay. And then we input all the information. C naught is from here, and S is from here. Let's say this NS is 15, and then Q is from the top. Q is 50 kot berapa? Big Q. Where is the big Q? Oh, Q is a 50 kilowatt. Q is a 50 kilowatt. So this is a 50 kilowatt. 50 only. Then RPM, then 79.37. Then we get this value, which is from Q. This one. Why we directly use 50 instead of 50 10 to the power 3? Because this one is under kilowatt. Under kilowatt. Then we have a meter. Then from here, number of pole is 8. L is we don't know. So we just put it like this. So after solving the simultaneous equation as above, the main dimension of the stator D and L can be obtained as this one. So first equation, we have this one. Okay, where is the second equation? State that is the simultaneous equation. Oh, this one good. This one is a first equation. This is second equation. Am I right now? Yeah. So yeah. So this is one of the equation, right? D equals to 0.135 P squared. So we have two equation now. After we include all the information here, then we will have this equation. Then another equation is like this. Okay, so we have these two equations. Then we do some substitution. With D go into here. Then we have what is the value of the L. And after that, we use L, substitute into the D, then we'll get the D. So this is so-called after solving the simultaneous equation. Then number of stator turn is we use equation as well, flux per pole first. So have a look on the equation here, flux per pole, this one. Then we copy the equation and we use it. So whereby it's a pi d lb a vp. So substitute all the value, then we get this. After that, our B phase. After that, we find the top number of turns. This is number of turn of phase by using the equation this one. This equation can be obtained here. This EMF of the induction motor. Sorry, number of turn per phase. This one. Then we have we calculate the how much is that? 98.93. So we take it 99. Then given what's that? Oh, this one we already given the number of slot per phase is 3. Total number of stator slot is using this one. This one also by given by here. This number let me see. It's a 3 times 3 times 8. Total number of stator slots. 3 times, okay. This one is come from here. So now we have a number of a slot. Let's say number of a slot per number of the pole. Everything per number of the phase is 3. So we want to find number of slot, right? The number of the slot equals to 3 times number of the phase and times again number of the pole. So what is a phase? Phase is 3, right? Pole is 8. So this is the value, whereby it is the total number of a stator slot. Then we will go to total number of the conductor per phase we need to use. So we use 99 divided by 2. Why is 99 is here? Why they use 99? This is number of 99 times 2. Total number of conductor per phase. Number of conductor. Oh, okay. Wait saya pun pening sikit. Slot. Aha. Okay. Total number of conductor per phase. Why we do that is because if let's say we say that number of turns per phase, which means one turn go in and go out. This is called one turn. Then maybe second turn like this. Which means in one slot, we have two conductor. Conductor 1. This is conductor 2. If let's say we have a three turn, 1, 2, 3. Okay, which means we have a conductor 1, conductor 2, conductor 3. So same as well. Now we want to find the conductor per phase. So because this conductor is go and back, so we use 99 times 2, whereby one is going here, another one is going back. So that's why they use 99 times 2, whereby it's from where is it? This one. Number of conductor per phase. We use this equation. Z phase equals to 2 times kph. So which means it's this one. This one. After that, number of conductor per slot. So we just use 198 divided by 72. So how can we get 198? 198 is from here, divided by 72. Okay. So maybe it's quite difficult to understand it. So let's have a look. We use 198 divided by 72, which means number of conductor per phase. This one, number of conductor per phase. Okay, which is 192. Divide by number of stator slots. So which means it becomes number of conductor divided by number of stator times phase. How can we use this one? Is actually like this. How to transform into here? Use number of conductor times 1 is this one. Then use phase and number of stator, get this one. So it becomes the name of a number of conductor per slot. Number of conductor per number of slot here. Is actually this one is called number of slot. Okay, so we use 198 divided by 72, which is 3. So assume when we want to have a slot, 3 conductor per slot, which means if let's say we have a 2 slot, right? When we put like this and go back, we need to have a 3 conductor per slot. 1, 2, 3. 3 wire lah, 1 wire go there, then second wire, okay, then third wire, for example, like this. And then number, assume we have this one, we need to check whether it is correct or not. So we assume that is a 3 conductor per slot, which means this slot got 3 conductor. Then total number conductor per phase is actually slot times a conductor per slot. So if let's say we deduct slot and slot, it becomes a conductor lah. Then total number of conductor per phase is 72. 72 is from the bottom, this one, times 3, which is a 216, right? Which is 216, whereby if let's say we use 3 conductor for 1 slot, how many per phase? How many conductor per phase we have? Which is 216. If compared to here, it is a 198, which is much more than that lah. For sure, much more than that for a little bit, because we choose 3 which is higher than 2.75. And then the revised number of turn per phase will be 216 divided by 2, which is 108. In the very beginning, we use a 72 lah. 99. So this is how we do the calculation induction machine for induction machine on how to apply all the equation there, all the equation here. So any question for you guys? This is one of the PBL, problem-based learning. I think the bottom one I already discussed with you guys. Okay, so maybe I think we rest for a while, and then I'll be back in the 10 minutes. Okay or not? We rest for a while, then we come back in the 10 minutes. Okay, thank you, Aiman. So I off the record first.